Good afternoon, everyone. I, Anubrata Roy, along with my co-author Siddhartha Sarkar, Bhargav Das and Satish Kumar from ACSIR and CSIR-CSIO are presenting MLP-based early onset estimation of PGA during an earthquake. The presentation is as follows. First, introduction, then literature survey followed by the proposed method and resultant discussion, then observations from the research and references. So first, introduction of earthquake early warning. We know that earthquake is a natural hazard. The earthquake consists of mainly two type of waves. First, there is primary wave, which is fast and reaches the sites earlier. Then there is S waves, which is slow comparatively, and it is the main cause of the destructive tremors. So in earthquake early warning, what happens? The seismometers or the seismic sensors detect the initial tremors or P waves. Then these recordings are sent to an early warning center or central server where the decision is made whether a warning should be generated or not. Based on this decision, warnings are sent via electronic medias like TV, computers, radios and cell phones. In the left side, we can see the human casualties from the last century by earthquake, which is much greater than any other natural hazards. And at the right side, the significant earthquake are plotted since the Richter scale was developed. So it is of utmost importance to develop EEW for hazard mitigation. In the EEW scenarios, there are basically two types of scenarios. First is conventional scenarios, then non-conventional scenarios. In conventional scenarios, there are regional earthquake early warning in which there is a seismic network. Based on the feedback of the network, detection of earthquake and location is determined. Also, magnitude estimation is done by this seismic from this regional earthquake called EEW. In onset earthquake early warning, there is a single node in different types sites. From this, early ground motion estimation or peak ground motion prediction can be done. Then there is non-conventional scenarios like cyber-social seismic networks or continuous GPS-based EEW. There are different research works pertaining to EEW using neural networks. As we can see, PGA estimation, neural network-based seismic detector, on-site earthquake early warning systems, seismic signal or noise discrimination, earthquake magnitude estimation. Various n number of works has been done till date. So from these literature survey, we can formulate the research gap, which is as follows. First, the dependency on the source parameters like earthquake location estimation, which is controlled by the magnitude estimation, which affect the site specific ground motion estimation. And maximum literature follows the magnitude or PGA estimation, which uses the features basically as source parameters. And uncertainty magnitude or site estimation, most of the literature uses GMP or ground motion prediction equation and attenuation models, which is required for warning level PGA estimation, but that is different for different sites and locations. So our objective will be to evaluate the performance of MLP based or multilayer perceptron based neural network to estimate PGA from initial P wave features. As you can see, this is the P wave. Around these features are selected, and based on these features, the MLP network determines the PGA. So for this, the dataset is prepared. The dataset is basically collected from the KNet, or Kyoshin net, operated by NIED Japan. From the dataset, the data extraction and conversion is done. Then data cleaning is done, like denoising, and the data is cleared when there is missing header or phase information. And from the phase onset file, there are ground truths of P onset that is generated by seismologists. These attributes are amalgamated, and there is a NoSQL database formed with the metadata of earthquake records and the triaxial accelerogram data. This is the characteristics of the Japan earthquake data of 2000. Basically, there are 163 number of events containing 2181 number of records. As you can see in the distribution, most number of earthquake records lies in the range of magnitude between 3 to 6. A fewer number of records exist that are greater than 7 or greater magnitude. Likewise, this is the magnitude distribution with respect to records, and this is the source to sensor distance distributions with respect to records. Total 33 number of features are used for this PGA estimation purpose. There are initial features like CAV, mean spectral magnitude, and higher order statistical features like skewness, kurtosis, ST by LTA, and there are triaxial features also. The features from 1 second window around the P onset up to 7 second delay from the P onset are extracted from the data. As we can see that these first 1 second, then second, then third 1 second, like so on, like 1 to 2 second, 2 to 3 second, 3 to 4 second. These 1 second records are used for feature extraction, and the uniform sampling of the feature windows are extracted with respect to its delay from the POA arrival. As you can see that the PGA or the output variable is highly skewed. So by using natural logarithm transformation, the PGA is transformed into log PGA where it is uniformly distributed. So the MLP predictor is now used for PGA estimation, where the input to the MLP predictor is the extracted features. So first, in this A figure, the features, the output variable is without log transformed, and in the B figure, the output variable of PGA is log transformed. So from the first figure, 33.33% of the total dataset is used as validation fraction. Here the R2 score is 62.09%, and MAE and MAC are 6.85 and 286.97 respectively, which is much larger, and where it is reduced while in the log transform value of PGA, where threefold cross validation is used, and the R2 score improved to 70.15%, and the MAE and MAC decreased to 0.41 and 0.27 respectively. MAE is mean absolute error and MAC is mean square error. The MLP BPNN based regressor is as follows. The hyperparameters of the MLP based BPNN is, there are a number of hidden layers. There are 2 hidden layers. First, there are 20 number of nodes, then there is 5 number of nodes. TANH activation function is used. Adam optimizer is used. The learning rate is 10 to the power minus 3. These are tuned hyperparameters. So we have tuned the hyperparameters according to the data and all. Then there is effect of delay from P onset of the predictor performance. Here we have taken uniformly sampled feature windows of 1 second, and we have moved over a new data, like from the first there is 1 to 2 second of data. The features are selected from these. Then we move to 2 to 3 seconds of data. So there is these 1 second of data contains another set of features. Like this, we have extended this up to 9 seconds and see what are the results for. In here, the target variable also log transformed. The performance measures we have used is R2 score, MAE and MAC. As you can see, the median error is lowest for the 5 to 6 seconds data. This 1 second data contains the lowest median error, and also the errors are decreasing up to the 4 to 5 seconds of data. Then the error are increasing. The performance measures are also increasing up to the 4 to 5 seconds, then it is decreasing. These are the table in which the different sample delay from the P onset, and according to the number of feature windows, how many feature windows were collected, and the performance measures according to the MLP regressor is shown. So we have further explored 8 to 9 seconds 2 seconds further up to 5 to 6 5 to 6 seconds. And we have shown that it is shown that the 5 to 6 second feature window has the best result, containing the R-squared score of 77.74% and MAE and MAC of 0.35 and 0.19 respectively. From the observations, it is seen that the logarithmic transformation improved the performance of the MLP based regressor, but there is still saturation of prediction near the higher and lower values of PGA. This can be removed by converting it into a classification problem. Like we can convert the PGA values into two classes. One is low class, for which there is no warning should be generated, and one is high class for which warning should be generated. Like this, this problem can be solved. And also uniform sampling of different duration yield best results during the 5 to 6 seconds. Finally, these are the references, and thank you.